Yet, this figure shows the titration curve of weak acid with a strong base depending on pKa values of weak acid. Okay, when pKa value is small, yeah, the weak acid approaches uh, the strong acid. Okay, so here the strong acid titration curve, yeah, is this one. Yeah? The initial pH is quite low, and at the equivalence point, which is 7, exactly 7, it increases a lot. Okay, so the step size, you look at that, for strong acid is greatest 1. But as the wiki the acidity of the acid is becomes smaller and smaller, yeah, this titration curve is looks like the same, but um, this step size, yeah, um, becomes the smaller. Okay, for example, uh, for weak acid whose pKa is 2, and this one is weak but rather strong, strong weak acid, right? So titration curve is more or less the same as the strong acid case. Okay, but when pK value increases to 4, and then now the initial pH is higher, yeah, it becomes higher and higher, and look at this titration curve change, right? And initially, when you add a strong acid, a strong base, and then initially pH increases rather rapidly, and then slowly, and then as approaching to the equivalence point, this pH value increases a lot. But this a larger step size becomes smaller and smaller as pKa value becomes larger and larger. Okay, for example, for pKa 6, there is a rapid initial increase of pH, and then slow down, and then also increases uh, as approaching to the equivalence point, right? Like that. So the step size is in this case is small, but still we can identify the equivalence point around here. Yeah, but for pKa of 8, you see, this one step size is very small, and for very weak acid, okay, like whose pKa is 10, you see, uh, you don't know, we don't know, the um, the equivalence points around here, all right, but it is not easy to identify the equivalence point. Okay, so here we can conclude that although weak acid and strong base, the reaction goes to completion. But if the weak acid Ka value is too small, okay, the titration is very difficult. Okay, and what about the concentration dependence on the titration curve? Concentration the dependence. Okay, this one shows the weak acid HA whose pKa is 5. Okay, when weak acid concentration is higher, like 20 millimolar, and then we have a very clear this titration curve. But as the weak acid concentration becomes smaller and smaller, okay, smaller and smaller, and then this step size becomes also smaller and smaller, right? So, for example, 2 millimolar HA, the titration curve here, okay, we start from here, and the step size becomes smaller. Okay, so for example, the very low concentration of weak acid, okay, 0.002 millimolar. Yeah, this is titration curve. So it is not easy to identify the equivalence point. So also we can conclude that um, although the pKa and Ka for weak acid is it has a reasonable value, but too low concentration, makes titration very difficult. Okay, so here it is not recommended to titrate an acid or base when its strength is too weak or its concentration is too dilute. Okay, yeah. Now let's consider the titration of weak base with a strong acid. The situation is exactly the opposite. Okay, opposite case of weak titration of weak acid with a strong base. Okay, the reaction here we have to consider uh, the reaction. The P is weak base. Okay, plus proton H plus is a strong acid. Okay, uh, this one also it goes completion. Okay, goes to completion because the equilibrium constant for this reaction is very high. Okay, so like weak acid case, we have four regions of a titration curve. The first one is initial pH. Okay, in the case, this B now reacts with water and becomes produce pH plus cation and OH minus anion. Okay, since it produces anion here, hydroxide ion, so this one acts as a weak the base. Okay, now we put X for produce the hydroxide and pH plus concentrations. Okay, so we can solve uh, this equation. Okay, and the second region is the before the equivalence point. In the case, there is a mixture of P and pH plus. Oh, aha, this is the purple, okay, made of P and pH plus. Look at that. Before the equivalence point, the moles of added proton is what? Hmm? The smaller than the initial moles of B. So in solution, there are P and pH plus species. So that is a buffer. Okay, and then we can apply Henderson-Hasselbalch equation. pH equals pKa. You see, you have a you need to be very careful. Okay, in this to apply Henderson-Hasselbalch equation. So you usually we here write pKa. Okay, but now we are dealing with B. Okay, weak base. So pKa means the pK value for this acidic form pH plus. Okay, and plus log. The numerator is P concentration of species P, and denominator is a concentration for species pH plus. Okay, and when uh, the added strong acid volume is exactly the half of equivalence point volume, right? And then these two concentrations are the same. So log this 0 1 is 0, so pH becomes pKa. Okay, this relationship applies. Okay, and so the region is at the equivalence point. At this point, all B becomes pH plus. So in solution, there is virtually no B nor proton species. Okay, only pH species is present, and then this pH species now undergoes um, dissociation to produce B and proton. Okay, in this case, Ka value equals Kw divided by Kb. Okay, and then we write this equation. Yeah, right. Yeah, solve for proton concentration, and the fourth region is after equivalence point, and then in solution we have excess proton concentration. Okay, so we only calculate this proton concentration, right? Yeah, that's it. Then here is an example. Okay? Let's consider titration of 25 milliliters of 0.08364 molar pyridine with 0.1067 molar hydrochloric acid. Okay, as you know, this is pyridine, right? Pyridine has a nitrogen atom in its structure, and this nitrogen atom there is a electron pair. So this is base, okay, and um, proton species can be bound to here, okay, to nitrogen. Okay, this pyridine has a the equilibrium constant Kb, which is 1.59 times 10 to minus 9. Okay, and Ka for this conjugate acid is Kw divided by Kb, and it gives 6.31 times 10 to minus 6. Okay, yeah, so pKa is 5.20. All right, yeah. So now find pH when Va added strong acid volume is 4.63 milliliters. Okay. Mm. To solve this problem, the first thing we have to do is to find out the equilibrium, uh, the volume of at the equivalence point. Okay, let's calculate first. You know, equivalence point volume here. Yeah. Uh, so the number of moles is the same, and the numerator is the volume times the concentration, and then divide by a strong acid concentration, and the value is 19.60 milliliters. Okay, this is the equivalence point volume. But since we only added this amount of volume, so this is now situation is before the equivalence point. Okay, and then how do you calculate pH? We use this Henderson-Hasselbalch equation. pH equals pKa plus log. Okay, now uh, you know let's go the easy way. Okay? This let me see. Um, in order to arrive at the equivalence point, we need 19.60 milliliters. But since only 4.63 milliliters is added, okay, the rest still this amount of P form, okay, 19.60 minus this volume, okay, and then this one produce this pyridinium ion is what? That is the added volume of strong acid. Okay, you understand? Yeah? So we don't need to calculate the concentration. So we need only to calculate uh, how long the distance between the added volume and the equivalence point, right? And then also, produced this one is proportional to the added the strong acid volume. Okay, this is a very clever way, and pH is 5.71. All right, that way we can very easily calculate uh, the pH. So the next topic is titrations in diprotic system. Okay, many acid or many bases are diprotic. Okay, for example, diprotic acid like oxalic acid, it dissociates in two steps, or some species mm, accept protons stepwise. Okay, uh, let's consider a special typical case. Okay, here let's say this P weak base P is what? Diprotic base. which means this B reacts, protons, stepwise. Okay? First, B reacts with strong acid to become pH plus, and then pH plus also accept another proton to become pH 2 plus. Okay, this is a very usual case. Okay? Here is the example: 10 milliliters of 0.1 molar B. Yeah, this B is titrated with 0.1 molar strong acid, hydrochloric acid. Okay, here pKb1, let's say, is 4 and pKb2 is 9. Okay, and we immediately know pKa1 is what? pKw, which is 14. 14 minus pKb2, which is 5. Okay, and pKa2 equals pKw minus pKb1. Okay, 14 minus 4, which is 10. Okay, now we will use these pKa values, yeah, in order to use Henderson-Hasselbalch equation. Okay, okay, since this weak base accept, the protons, the step by step. So here uh, we uh, we can imagine this type of titration curve. Here we have, two, since one titration curve and, subsequent titration curve two. All right. So there are, one, two, two equivalence points. Okay. The first one, C is the first one, and E is the second one. Okay. So we have to calculate two equivalence points. All right. Let's calculate the first equivalence point here. Yeah? We only consider this first equation here. Yeah, that is very easily calculated. Okay, and 10 milliliters times uh, zero point 0.1 molar divided by, this HCl concentration, 0.1. So answer is 10 milliliters. Okay, right. So here this is the first equivalence point. And second equivalence point is simply 2 times of the first equivalence point. Why? Look at that. The second this reaction is what? Exactly same as, the first one. Okay. Mm. So volume you need to complete the second reaction is just as twice our first equivalence point. So we don't need to calculate anymore. Simply we calculate the volume for the first equivalence point, and then we simply multiply by 2 to get the second equivalence point. Okay, which is now 20 milliliters. Okay, yeah, very easy so far. All right, here uh, let's consider this blue curve. Okay. Mm. The point A is what? That's the initial pH. Okay. To calculate initial pH, let's only consider this first um, equilibrium. Okay. B now react with water to produce pH plus and hydroxide ion. Okay. In this case, Kb1 is 10 to minus 4, and then we solve this equation, and then we get x value is 3.11 times 10 to the minus 3. Yeah, that's the hydroxide ion concentration. Okay, so proton concentration we can calculate, and then we get pH now is 11.49. Okay, this one is initial pH, yeah, before the strong acid is added. Okay, now let's calculate the pH at point B. Now this point B is exactly the middle point, middle way before the equivalence point. Okay, so V equals 1/2 of VE. Okay, this is halfway between A and C. So when we apply this uh, Henderson-Hasselbalch equation, concentration of P and pH plus are the same. Okay, and then pH is simply pKa2 here. Okay, now pKa2 is what? 10. All right, here that's the pKa2 value. All right, yeah, very easy. And let's now calculate the pH when uh, 1.5 ml of HCl is added. Okay, 1.5 ml. So the easy way is to we find 1.5 ml is here. Okay, and this equivalence point is 10 ml. Okay, so since we added 1.5 ml here, the rest 8.5 ml correspond to what? P. Okay, P, and added 1.5 correspond to pH plus. So we can calculate the ratio. We don't need to calculate any volume since we need only this concentration ratio. Okay, so from this titration curve we can easily find out this ratio, which is now 8.5 divided by 1.5. So pH becomes 10.75. All right, and let's calculate pH at point C here. This is first equivalence point. Okay, at this point the species is only what? pH plus. Okay, pH plus here. Now this pH plus is intermediate form. Okay, intermediate form. This pH plus is in between P and pH 2 plus. Okay, so in this case in the previous chapter we learned how to calculate the pH for the intermediate form. Okay, we use this equation. All right, proton concentration is approximated by this equation. All right, here K1 and K2 are for pH 2 plus. Okay, yeah. Let's calculate. Okay, to calculate uh, uh, first you have to calculate F value, right? F is the formal concentration of pH plus form. Okay, since uh, the strong acid is added, the volume increased. All right, now the initial original concentration of P is 0.1 molar, right? And then volume increased from 10 to 20. Okay, so the pH plus concentration is 0.05 molar. Okay, and we use this number and insert to this equation. Okay, here now proton concentration is given by this equation, and K1 is what? 10 to minus 5, and K2 is 10 to minus 10, and F is 0.05. Okay, and K1 is 10 to minus 5, and Kw is 10 to minus 14, divided by K1 plus F. Okay, and then this value is 3.16 times 10 to minus 8. So pH is 7.5 here. Okay, that's the pH at the equivalence point. Okay, but you remember if we more approximate this equation, and then the pH is the half of pKa1 and pKa2. Okay, now since pKa1 is 5 and pKa2 uh, is 10, so middle point is 7.5. Okay, so this approximation in this case uh, holds. Okay, yeah, but I strongly recommend you use this equation, not this equation. Okay, okay, now calculate the pH. Okay, point D, which is the middle point between first and second equivalence points. Okay, in this case, since pH plus and pH 2 plus, these species both are present. So this is a buffer, a second buffer. The first buffer is formed between A and C points. Okay, and here now let me see. Point D is exactly the halfway between the C and E. Okay, in this case, pH plus concentration is the same as pH 2 plus concentration. All right, and applying again the Henderson-Hasselbalch equation. All right, here pH equals pKa1 plus log, log of this ratio. Okay, this two species ratio. Since at point D, the two concentrations are the same, so pH is directly pKa1. In this case, pKa1 is 5. All right. But what if you add 17.2 ml of strong acid? No, 17.2 ml is past the first equivalence point and is around here. Okay, around here. So that is before the second equivalence point. So now, from 10 to 17.2 ml, this added, that corresponds to what? That's pH 2 plus, okay, 2 plus species, and the remaining amount, which is 10, this distance is 10 minus 7.2, okay, or this is 20 minus 7.2. That corresponds to the concentration of pH plus. Okay, so this ratio in this case now given this way. So when 17.2 ml of strong acid is added, pH is given by this equation. Very simple, and which is what? Wow, I didn't calculate here. Okay, but you understand, the concept. All right. Okay, and then finally let's consider the pH at this one, second equivalence point. At this point, all the form is only pH 2 plus. Okay, now this one acts as what? Weak acid. Okay, let's let's calculate formal concentration of this species. Okay, and this one is the concentration. Original concentration is 0.1 molar, but since the strong acid was added by 20 ml, so initially 10 ml was there, so total volume is 30 ml. Okay, so this is the dilution factor. Okay, so formal concentration of this form is 0.0333 molar. Okay, and then we use this equation for the weak acid, and then we solve for x. Now x is proton concentration, and we get this value of x, and pH is 3.24. Okay, so now the concept is the same as monoprotic acid or base cases. Okay, the only difference is that for diprotic acid or base, right, the titration curve, we find two equivalence points. Okay, so depending on which when you add a strong acid or base, first we have to locate that position on this graph, and then we can calculate very easily. All right, and then the final I'm sorry, the final one is the beyond this second equivalence point. Okay, and what is the main species beyond the second equivalence point? Since we added strong acid, the proton is the main concentration. All right, let's assume you added now 25 ml of strong acid. Now it's here, around here. Okay, and that means what? 5 milliliters of strong acid was added additionally. So we only consider the 5 ml. Okay, the initial proton concentration was 0.1 molar, right? And then it was diluted by this amount, initially 5, but now the final concentration is 35 ml. So in this case, proton concentration becomes 1.43 times 10 to minus 2 molar, and pH is 1.85. All right, yeah. Um, so easy, okay? It's not very difficult. Okay? Uh, Here, blood and the point. Yeah, blood and the point is what? That means that sometimes it is difficult to locate the end point. Okay? End point is not seen. Why? Okay, look at that. The blue titration curve shows very distinct end point. Okay, the first end point or equivalence point is very easy to locate, and second one is also good to locate. But the this black curve, yeah, in this case, the second, the equivalence point or end point is not very distinct. Why? There are several cases. First, the pH is too low or too high, okay? Or when pKa values are too close to together and the points are obscured, okay? So no clear break at end points, okay? Here, this one we can rather easily locate this end point, right? Because there is a big change in pH. But in this case, black curve, you see, the second end point is not clear, okay? The example is the titration of ribonuclease. At the outset of this chapter, we saw the titration of ribonuclease. So there are, many endpoints. So it is not easy to locate, okay, individual endpoints.